Good morning or good afternoon, depending on where we are. We are continuing with our thermodynamics lectures. Today, my name is Professor Duke Orata. Let's look at heat flow across a boundary layer. Heat flow equation in a boundary layer. In a boundary layer. Now, our system is one where we are going to have a plate, and that plate has a width, a unit width, and of course, the length is dx. Let's call it dx, and it is bound by some planes. That is, which you can call AA, another one BB. So, of course, by implication, there's a plane AB, and of course, A prime, A double prime. Let's just draw the schematic for that. So we have our plate. So we have these planes AA, BB, and they're saying dimension is dx. We have A prime, A double prime, and of course, by implication, it's implied that we have also plane AB. And let us say that, for example, that we have both thermal boundary layer and we also have the velocity boundary layers. As we are showing here, let's call that the thermal boundary layer. Thermal boundary layer. And its thickness, let's call it, let's just call it sigma t. And the velocity boundary layer, let's say the thickness is sigma. And up to the surface there, let's say that length is L. Let's call it K. Or let's call it L, because we'll have other values which will be K. And so we have our surface there. So we have these two planes, AA, BB. Now, this system is open. Remember, in thermodynamics, we talked of three types of systems, which I will encourage you to look at our very early lectures. We say that in thermodynamics, we have an open system where matter can be transferred between the system and the surroundings. We have a closed system where matter cannot be transferred between the system and the surroundings. And we have an isolated system, which is a closed system. In other words, matter cannot be transferred between the system and the surroundings, but it's also not in thermal or mechanical contact with the surroundings. Otherwise, there's no heat transfer across its walls or work done across its wall. And what is a system? Remember, system is that part of the universe which you have a special interest, and where you make your observations are the surroundings. So you fit your description in those kind of definitions. Now, when mass is transferred across the plane AA and it exits across the plane BB, now you will find that the difference between the masses, the mass which entered and the one which exists, that difference, the mass which exited through the surface AB. So we are saying that the system is open, therefore matter can be transferred. Matter can be transferred. And we are saying that the mass transferred across A, the one which enters through A leaves at B, that difference is the mass which has gone through AB. That difference, one which has gone through AB. So if we just represent those masses systematically, let's say sigma m at AA minus sigma m at the plane BB, that will be the same as that has exited through the plane AB for sigma m. So these sigmas, we're just talking of the masses. Now, we assume the steady state energy equation, and I encourage you again, I repeat, it's important to try and follow up, build up this concept systematically. We have talked about all this in earlier lectures, so I encourage you to just look at them. The steady state energy equation. Remember, the steady state energy equation was given as dH plus dc squared over 2 plus d dz is equals to dq plus or minus dw. And this element here represented the potential energy. This represented the kinetic energy. And this is the enthalpy. Enthalpy, this is kinetic energy, and that is potential energy. So if you look at specific enthalpy and kinetic energies, we can now assume, let us assume that in our case, the potential energy does not change significantly. In other words, there's no significant change in the datum levels. So we can talk of our system here. We can ignore the potential energy, assuming no change in the datum level. Then we can assume potential energy is literally zero. So we are left with dH plus dc squared over 2 is equals to dq plus or minus dw. But when you are deriving the steady state expression, remember we said that for that unit element, volume element, there was balance in the work done by it and the work done on it, that unit element. So in other words, you can assume that there's no work done on it because they are all balanced out. The work done on it and the work it does and the work done on it balance out. So they cancel out. So we assume that in this particular system, that particular mass work does not do work, neither does work is work done on it. We assume work not done by the mass, or not done by the mass or on the mass. So we can say that dW is 0. So you have made two key assumptions. Potential energy you have assumed is 0, and that there's no work done on that particular mass, neither does it do work. So we have assumed it's 0. I've assumed it is 0. So now let's proceed. So, for the plane A, we can now say that sigma of that mass is h plus u squared over 2. Remember c and u, we are just using them. C, u is all velocity. So, for this particular case, for AA, you have that. Similarly, for BB, you have sigma m h plus u squared over 2. And we have said the difference between that AA minus for BB, let's just call this quantities here, we just call this, let's just call that A, and let's call that quantity B. BB is equals to what we have in the plane AB. Let's call that C. Now, let's work with these particular quantities. What do we get? So we are having that for plane AA. So these quantities here, we have for plane AA, remember we have dH and we have du squared over 2. So when now we integrate them, this is just a summation. When we now integrate, it's over large intervals, so that's the total sum over the intervals. So for AA, what are we going to have? So remember, we have our parent equation, that is dH plus du squared over 2 is equals to dq plus dw, which we have already said is 0. So this is dq. So let us put the expression for the plane AA, for the plane BB, and of course AB. So for plane AA we have, therefore, we will have integral, of course, of dH plus the integral of u squared over 2. Now, there's an identity which we need to use to make our lives a bit easier. And that identity which we are going to use is that for du squared over 2, that's the same as the integral of u du. Because remember, u to the n integral is u n plus 1 by n plus 1 plus c. So in the same way, that's raised to power 1. So if you integrate it, it will be u squared over 2. So in place of du squared over 2, we'll put that integral. So we'll have the integral of u dy from 0 to L, remember? And then we have plus, this is for AA, and then for BB we have again the integral dH plus the integral 0 to L u dy, and remember we said there's a difference. The mass which entered and left are not the same, and that difference is what went through the plane AB. That captured the sense that we have the x integral of u du dx 0 to L. So that the difference here, this difference which we have there, it gives us the expression for BB, which will now be, for BB now, what we have this difference here is that quantity there, this particular quantity here. That's the main difference. Therefore, what are we saying? For BB, therefore, using still our identity, for BB, same way, which you have sigma m h plus u squared over 2. And now we know that it is dH integral, of course, from some temperature at the wall, let's call it TW, T in solution, let's put the limits, TW, TS, the wall, T solution, TW, T solution. Very good. And so what do we have there? So we have plus dx integral of 0 to L u du dx. But remember that generally dH is equals to Cp. Specific enthalpy is rho Cp dt. Remember that. Density, that is isobaric. Cp is isobaric heat capacity. That is density, that's isobaric heat capacity. So let us see how we now apply this. And remember, all this has to do with specific enthalpy and specific kinetic energy is all equal to the heat transferred. Now, say all that is equal to the heat transferred. That is rho Cp temperature, that is Ts minus Tw, plus d dx, L u du dx is equals to dq. Because we say that there's no work done on that mass, neither does it do work, nor is work done on it, and the balance, they cancel out. So we assume that the work done on it is 0. So we have this expression. So at this particular point, in terms of heat transfer, we will use the Fourier's law. Remember, just look at our earlier lectures, Fourier's law, which I believe you're now pretty familiar with, and you know what it is, that it is Q, Fourier's law Q is equals to minus K A dt dy. And what is our area? Remember, we said the plate length is dx, the width is unit, so it's dx. So we can equate those there. So we have rho Cp Ts minus Tw plus d over dx to L u du dx is equal to minus K. Area now we said is dx, and of course the temperature dy is equals 0. So if we simply, remember K is thermal conductivity, if we simply rearrange these quantities, let's divide throughout by rho Cp, dividing throughout. Let's divide throughout, simplified by rho Cp Ts minus Tw. Let's divide throughout by that quantity there. Divide with that. So what do we get? Things are now taking shape. That will be 1 plus d dx rule L u du dx is equal to, I think let me use the full board so that I don't break it down. We are saying we have 1 plus d dx integral from L 0 to L u du dx is equal to, dividing this quantity both sides, so we have minus K over rho Cp into Ts minus Tw minus Tw dx dt dy y is equal to 0. Let's call this temperature difference, let's just call it theta. Make our lives easy. Let's call it theta. And you notice already this quantity, we are familiar with it. We saw this particular quantity in Fourier's number. This quantity here, we saw it in Fourier's number. When we worked with the Fourier's number and Biot number, we saw that that was the thermal diffusivity, alpha. This quantity is alpha, which we call thermal diffusivity. If you remember, we found it was in Fourier's number. Let's look at our earlier lectures. And so, what are we saying? We're saying that 1 plus d dx 0 to L u du dx. I'm up there, I'm going to overlap that. So that's 1 plus d dx to 0 to L u du u du dx is equals to minus alpha, that is the thermodiffusivity, over theta, which we have already said is that difference there, dx to dt y. This, if we now assume that this quantity is much greater, for example, than that quantity there, if we assume that it's much greater than 1, then we'll have d over dx 0L dx equals minus alpha over theta dx dt over dy y is equals to 0. This is the heat equation. Across a boundary. That's a heat equation across a boundary. Very important. Now we have that bounded plane where we have two planes. We have our plane bounded by those two planes, AA and BB. And of course, it's implied we have AB, but that surface there, surface of the boundary layers. And we have said that the plate side length is dx and its unit width. And you have seen how we have proceeded. We have proceeded with it when you use steady state expression, where we have assumed there's no change in datum level, so the potential energy is basically 0. Then the specific enthalpies and kinetic energies expressions are the ones left, and that is equal to the heat transfer to the system, because we assume there's no work done on those masses. They don't do work, neither is work done on them, and you have just profiled that in terms of our derivations of steady state equations. And we have seen that in that particular context now, for the heat transfer, of course, you know that we use the Fourier's heat equation, and we are able to equate the two, and this is the expression which gives us the heat equation for flows across boundaries. So we'll stop at that particular point. We'll pick up with other topics in thermodynamics next time.